Drop something, a coin, a key, your phone into the blankets. It falls, the way everything has always fallen, the way you have watched things fall 1,000 times without once wondering why. Gravity is the most familiar force in your life, and also, by a wide margin, the weakest in the universe. So weak that a refrigerator magnet can beat the pull of the entire planet and lift a paperclip clean off the table. It is the one force we still cannot fit into the physics of everything else. And here is the part almost no one knows. For 30 years, physicists nearly abandoned the study of gravity altogether. What brought it roaring back was not a university and not a government. It was the private fortune of two men who were convinced they could build a machine to switch gravity off. Tonight, the strange and true story of how a war against gravity accidentally gave us black holes, gravitational waves, and the most complete picture of reality we have ever drawn. Before we begin, if a slow, true story is how you like to drift off, a quiet like or subscribe genuinely helps the channel grow. It's a small thing for you, but it means the world to me. Now, let's begin. Part 1. The year gravity became geometry. There is a force at work in the room with you right now, and you have never once felt it switch off. It is holding you against your bed. It is holding your bed against the floor, and the floor against the ground, and the ground against the enormous stone heart of the planet, turning slowly beneath you. You have lived your entire life inside its grip, and you have grown so used to it that you no longer notice it at all. And yet, of the four fundamental forces that build reality, this one is the strangest, the weakest, and the least understood. Tonight, we are going to follow the true and almost unbelievable story of the people who tried to defeat it, and of the secret they accidentally uncovered along the way. To understand that secret, we have to begin in the year 1915. The First World War is grinding across Europe. In the factories of Michigan, the Ford Motor Company is building its millionth Model T. And in Berlin, a 36-year-old patent clerk turned professor is finishing a set of equations that will quietly rearrange the meaning of the word gravity forever. His name, of course, is Albert Einstein, and the theory he completes that year is called general relativity. For more than 200 years before that moment, gravity had a single, confident explanation, and it belonged to Isaac Newton. In Newton's picture, gravity was a force, a kind of invisible rope reaching across empty space, tugging every object toward every other object. The sun pulled the earth pulled the moon, the earth pulled the apple down from the branch. It worked with astonishing precision. It let us predict eclipses centuries in advance, and, much later, sail spacecraft to other planets. For 2 centuries, Newton's rope was simply what gravity was. Einstein looked at that rope and asked an uncomfortable question. How does the sun reach across 93 million miles of empty vacuum and take hold of the earth? There is nothing between them. No string, no rod, no visible connection. Newton himself had been troubled by this. He had described how gravity behaves with perfect accuracy, but he had quietly admitted that he could not say what it actually was, or how it managed to act across all that emptiness. For 200 years, physics had used the rope without ever finding where it was tied. Einstein's answer was to throw the rope away entirely. Gravity, he proposed, is not a force reaching across space. Gravity is the shape of space itself. Imagine the whole of space and time woven together into a single smooth fabric, a 4-dimensional structure that physicists call space-time. Now imagine that every object with mass presses down into that fabric, the way a heavy ball presses down into a stretched rubber sheet. The sun, being enormous, makes an enormous dent, and the earth, sweeping around the sun, is not being pulled by any rope at all. The earth is simply rolling along the curved slope that the sun has carved into space-time, following the straightest possible path through a landscape that has been bent. This is the idea that changed everything. Matter tells space-time how to curve, and the curve of space-time tells matter how to move. The apple does not fall because a force reaches up and grabs it. The apple falls because the Earth has bent the space around it, and falling is simply what it means to move naturally through bent space. When you feel gravity holding you to your bed, what you are really feeling is the shape of space-time, sculpted by roughly 6 trillion kilograms of planet, gently insisting on your path. And here is the first quietly astonishing thing about this force, the thing that makes the rest of our story possible. For all its grip on you, gravity is, by an enormous margin, the weakest of the 4 fundamental forces of nature. It does not feel weak, because the entire Earth is pulling on you at once. But consider a small, ordinary magnet, the kind that holds a note to your refrigerator. That little magnet, using electromagnetism, can lift a paperclip straight up off the table, which means its tiny field is defeating the gravitational pull of the entire planet acting on that paperclip. The whole Earth pulls down, and a magnet the size of a coin pulls up and wins. That is how feeble gravity is compared to the other forces. It is weaker than electromagnetism by a factor so large it barely fits in words, a 1 followed by roughly 36 zeros. Gravity only rules the large-scale universe because, unlike the other forces, it never cancels out and it never turns off. It only ever adds. Every scrap of matter pulls on every other scrap, always, and given a planet's worth of matter, or a star's, or a galaxy's, that relentless, feeble, one-directional pull becomes the master architect of the cosmos. This strange combination, almost nothing up close, and yet the ruler of everything immense, is the first clue that gravity is not quite the simple force we were taught it was. It sounds like poetry, but Einstein's theory made a hard, testable prediction. If mass really bends space, then even light, which has no mass in the ordinary sense, should follow those bends. A ray of starlight grazing the edge of the sun should be deflected, its path curved by the dent the sun makes in space-time. Newton's theory predicted almost no such bending. Einstein's predicted roughly twice as much, a deflection of about 1 3/4 arc-seconds, a tiny angle, smaller than the width of a coin seen from 2 miles away, but a measurable one. In 1919, 4 years after the theory was complete, an English astronomer named Arthur Eddington sailed to an island off the coast of Africa to test it. He waited for a total solar eclipse, the one moment when the moon blocks the sun's blinding light and the faint stars near its edge become visible. He photographed those stars. He measured how far their apparent positions had shifted, and the shift matched Einstein, not Newton. The starlight had bent around the sun by exactly the amount that a curved space-time demanded. The news traveled around the world in days. Newspapers announced that the heavens had been reweighed, that a new theory of the universe had dethroned the old one. Einstein, almost overnight, became the most famous scientist alive, the human face of a revolution in thought. For a few short years, gravity was the most glamorous subject in all of physics. Bright young minds wanted to work on it. The curvature of space-time, the bending of light, the possibility of an expanding or contracting cosmos, all of it shimmered with promise. It felt like the beginning of a golden age. And here is where the story takes its first strange turn, the turn that almost no one outside the history of physics knows about. That golden age did not arrive. The excitement did not build. Within a decade or so of Einstein's triumph, the study of gravity began, quietly and steadily, to fade. The most beautiful theory in physics was about to be left in a drawer, half forgotten, for the better part of 30 years. Why? That is the first mystery we have to solve, because everything that follows, the 2 obsessed millionaires, the flying saucers, the high-voltage laboratories, the conference room where gravity was reborn, all of it grows out of the simple, baffling fact that after 1915, physics had a perfect theory of gravity, and then, astonishingly, chose to walk away from it. To feel why that happened, you have to understand what else was happening in physics at exactly the same time. Because while Einstein was bending starlight around the sun, a second revolution was gathering, one that would prove louder, faster, and far more seductive than the quiet geometry of curved space. It was the revolution of the very small, and it was about to swallow the attention of an entire generation, leaving Einstein's masterpiece sitting in the dark, waiting for two men who were not physicists at all, one of whom had come to think of gravity not as a beautiful idea, but as a murderer. We will get to that man soon, but first we have to walk into the decades when physics forgot gravity and understand how the most celebrated theory of the century became a place almost no serious scientist wanted to go. Part 2. The decades when physics forgot gravity. Historians of science have a quiet, almost sad name for the years that followed Einstein's triumph. They call it the low water mark of general relativity. It is the long stretch, running roughly from the middle of the 1920s to the middle of the 1950s, when the most beautiful theory in physics slipped to the margins and very nearly drowned there. For about 3 decades, gravity was something a serious, ambitious physicist was advised to avoid. To understand the secret at the heart of this story, you first have to understand how that happened, because a field does not go dark for 30 years by accident. The first reason was simply that something more exciting arrived. In the same years that Einstein was finishing general relativity, a very different revolution was breaking open, and it concerned the world of the very small. Quantum mechanics, the physics of atoms and electrons and light itself, exploded across the 1920s in a burst of discovery so rapid it left everyone breathless. Every month seemed to bring a new result, a new equation, a new impossible fact about the behavior of matter at the smallest scales. Electrons that behaved like waves, light that arrived in packets, a world governed by probabilities rather than certainties. The crucial thing about quantum mechanics, for a young scientist trying to build a career, was that it was generous. It handed out solvable problems by the hundred. You could take a real atom, apply the new equations, and calculate something that a colleague down the hall could then measure in a laboratory. The theory made predictions you could check by Thursday. It rewarded effort with answers, and answers with reputations. An entire generation of the most gifted physicists in the world poured into the quantum world, because that was where the discoveries, the jobs, and the glory were. General relativity offered almost the opposite bargain. Einstein's field equations are, to put it gently, brutal. They are a tangle of interlocking relationships, 10 of them woven together, and they are non-linear, which is a technical way of saying that they fight back. In most of physics, if you have 2 solutions to a problem, you can add them together and get a third. Einstein's equations refuse this courtesy. Gravity, in his theory, is a source of more gravity. The energy stored in the curvature of space itself bends space further, so the equations feed on themselves, and solving them exactly is possible only in a handful of clean, idealized cases. For decades, working with general relativity felt less like doing physics and more like wrestling a mathematical animal that did not want to be understood. And then there was the greatest problem of all. General relativity had almost nothing to measure. Einstein's theory made only a small number of testable predictions, and by the 1930s, they had mostly been checked. Starlight bent around the sun. The orbit of Mercury drifted by a tiny amount each century, exactly as the theory required. Light climbing out of a gravitational field lost a little energy. That was more or less the entire experimental menu. The differences between Einstein's predictions and Newton's were so minuscule, so hard to detect, that for most everyday purposes, Newton's old rope worked perfectly well. Why spend your life on a theory whose corrections to the older picture were too small to see? So the theory acquired a reputation. It became known as a kind of intellectual monastery, a place for a small number of devoted specialists, mathematicians really, who cared more for elegance than for experiment. It was beautiful, everyone agreed, and it was finished. There seemed to be nothing left to do. A student in the 1940s who told his advisor he wanted to work on gravitation would often be met with a gentle, discouraging silence. Gravity, he would be told, was a solved problem and a dead end. The action was elsewhere. The isolation this produced was very real and very lonely. The handful of physicists who kept working on general relativity through these years were scattered thinly across the globe, often the only person at their entire university who cared about the subject, corresponding by slow mail with a few far-flung colleagues, rarely able to gather in the same room. There was no thriving community, no steady stream of conferences, no sense of a field moving forward together. There was just a small, stubborn scattering of specialists, keeping a flame alive in the dark, many of them treated by their peers as slightly eccentric for bothering. It is one of the quiet tragedies in the history of science, a masterpiece of human thought, left mostly untended for a generation, not because it had been disproven, but simply because it had gone out of fashion and out of funding at the same time. Then the world went to war, and the second reason arrived, and it was even more powerful than the first. In the 1940s, physics changed from a quiet academic pursuit into an instrument of national survival. The atomic bomb, built by physicists working with the nucleus of the atom, ended the Second World War and announced to every government on Earth that the physics of the very small was now a matter of life and death. Money followed that announcement in quantities the field had never seen. Nations poured fortunes into nuclear physics and, soon after, into the physics of the even smaller particles hiding inside the nucleus. This flood of funding had a shape, and gravity was not in it. If you were a physicist in 1950 and you wanted a laboratory, a salary, graduate students, and a career, you followed the money, and the money led straight into particle physics. It led to accelerators, to the hunt for new particles, to the strange zoo of quarks and other fragments that the great machines were beginning to reveal. Governments were not interested in the curvature of space-time. They were interested in the atom, because the atom had just ended a war and might decide the next one. You can hear how completely gravity had vanished from the center of physics in a story from decades later. In the 1980s, one of the most respected physicists alive, Murray Gell-Mann, gave a famous talk in which he laid out what he considered the four great unsolved problems of physics. He listed questions about the underlying structure of particles, about why matter comes in the families it does, about the fundamental symmetries of nature. And listen to what is missing from that list. Quantum gravity, the problem of uniting Einstein's theory with the quantum world, the problem many people today would call the single greatest unsolved question in all of physics, does not appear at all. One of the leading minds of the era did not think it belonged among the most important problems. That is how far gravity had fallen. There is a lesson hiding in that fall, and it is worth pulling into the light now, because it will matter more and more as our story goes on. We like to imagine that science advances purely on the strength of ideas, that a good enough question will always find someone to answer it, that truth rises on its own merits. But scientists are human beings, with rent to pay and families to feed and careers to build, and where the funding flows, the research follows. This is not cynicism, it is simply how the world works. A brilliant young physicist in 1950 could love the curvature of space-time with her whole heart, and still, quite reasonably, choose to work on the atom, because the atom is where the salaries and the laboratories and the futures were. When a whole society decides, through the direction of its money, that one question matters and another does not, the map of human knowledge quietly bends to match. Gravity fell out of favor, not because it stopped being profound, but because the money stopped pointing at it. And that means, chillingly, that the shape of what we know is partly the shape of what someone, somewhere, was willing to pay to find out. Hold that thought, because it is the key that unlocks everything strange about what comes next. If research follows money, then the fate of a neglected field can be decided not by the scientific community at all, but by whoever is willing to open a checkbook, for whatever reason, sane or not, sound or not. And into the silence around gravity, checkbook in hand, walked a man with the least scientific reason imaginable. Now, sit with the strangeness of this for a moment, because it is the crack through which the rest of our story enters. Here was general relativity, arguably the most profound description of reality ever written down, a theory that would eventually give us black holes, the expanding universe, the warping of time, and gravitational waves. And for roughly 30 years, the professional physics community looked at it, decided it was finished and unfruitful, and let it sit in the dark. The universities were not going to save it. The governments were not going to fund it. Consensus had quietly closed the door. When a field is abandoned like that, it does not usually come back. Ideas go cold. The people who understood the hard mathematics grow old and retire without training successors. A generation of silence can become permanent. General relativity was drifting toward exactly that fate, toward becoming a historical curiosity, a beautiful thing Einstein once did, admired from a distance and worked on by almost no one. And this is the part that still astonishes the historians who study it. The theory was not rescued by a university. It was not rescued by a government, or an army, or a great scientific academy. It was rescued, against every expectation, by private money, by the personal fortunes of two American businessmen who were not physicists, who most scientists considered eccentric at best and ridiculous at worst, and who were chasing a goal that the entire field regarded as a fantasy. They wanted to defeat gravity. They wanted to build a shield against it, a machine to turn it off, and in pursuing that impossible dream, they would pour money into serious research on gravity at the exact moment the field needed it most. The first of these men had a reason for his obsession that was not scientific at all. It was personal, and it was rooted in grief. To understand him, we have to go back to a cold river in Massachusetts, and to the day a boy watched the water take someone he loved, and decided, in the long years afterward, that the true culprit was not the water, it was the force that pulled her down. Part 3. The Man Who Declared War on a Force. Roger Babson was born in 1875 in Gloucester, Massachusetts, into an old merchant family, and by the middle of his life he had become one of the wealthiest and most listened-to financial forecasters in America. He founded a statistical organization that pioneered the modern business of predicting markets, and he founded a college that still carries his name. He was not a scientist. He was a businessman of enormous confidence, and his confidence rested on a single idea that he had borrowed, of all places, from Isaac Newton. Babson was fascinated by Newton's third law of motion, the one that says that for every action there is an equal and opposite reaction. Most of us remember it from school as a fact about rockets and recoiling guns. Babson turned it into a philosophy of money. He believed that markets, like physical objects, obeyed action and reaction, that every rise must be balanced by a fall, that prices swung around a normal line the way a pendulum swings around its rest point. He drew charts based on this principle, and he trusted them completely. On the 5th of September 1929, he stood up and publicly warned that a crash was coming. The market dropped sharply that very day, a lurch that newspapers nicknamed the Babson break. Weeks later, the great crash of 1929 arrived in full, and Babson looked like a prophet. That single prediction sealed his fortune and his fame. He became a household name, a man whose newsletters were read by tens of thousands of investors, whose pronouncements moved markets, whose wealth grew to the kind of scale that lets a person build colleges and fund foundations on a whim. He would even, later in life, run for President of the United States on a minor party ticket without any real hope of winning, simply because he was the sort of restless, self-certain man who believed his ideas could reshape the world. This is important to understand about Babson, because the ordinary version of this story paints him as a harmless eccentric. He was not harmless, and he was not marginal. He was a wealthy, powerful, widely respected figure in American business. A man whose word carried weight. And when such a man decides to spend a fortune chasing an idea, the idea gets chased, whether or not the scientists approve. His confidence was total. His resources were enormous. And his target, chosen not by reason but by grief, was one of the four fundamental forces of nature. So here was a man who had built a fortune and a reputation on Newton's laws of motion. A man who thought about the physical world constantly, who saw action and reaction everywhere he looked. And this same man carried, underneath all his success, a wound that never healed, because Roger Babson's fascination with gravity did not come from curiosity, it came from death. When Babson was a boy, his older sister drowned. She went into a river near their home in Massachusetts, and the water took her, and she did not come back. Years later, in an essay he would title with brutal directness, Babson wrote about what he believed had really happened to her. He did not blame the river. He did not blame chance, or a current, or a moment of panic in cold water. He blamed gravity. In his own words, she was unable to fight gravity, which came up and seized her like a dragon and brought her to the bottom. Stay with that image for a moment, because it is the seed of everything that follows. To almost anyone else, a drowning is a tragedy of water and lungs and terrible luck. To Babson, it was a murder, and the murderer had a name, and the name was gravity. The force that Einstein had just recast as the gentle curvature of space-time, the quiet geometry that holds planets in their orbits, Babson saw as a predator that reaches up from the bottom of every river and drags the helpless down. He had watched it take his sister, and decades later, gravity would take someone else he loved. His grandson also drowned in 1947, and by every account, that second loss pushed the old man's obsession past the point of reason. Imagine the scene, not as a diagram, but as a moment lived. A cold river in Massachusetts, sometime in the 1880s. 2 children near the water on an ordinary day, and then the ordinary day breaks. A small body slips beneath the surface, and the surface closes over it, smooth and indifferent, and does not give it back. Somewhere in the long decades afterward, an old man sits alone with that memory, and instead of letting it soften into grief, he sharpens it into a war. He picks up a pen and writes the sentence that will define the rest of his life. She was unable to fight gravity. She was unable to fight it, as if gravity were an enemy that could, in principle, be fought. As if the right machine, the right shield, the right discovery might one day reach down into the water and hold the drowning up. That is the strange and human engine at the center of this story. We are used to imagining that science is driven by cool curiosity, by disinterested minds asking neutral questions. But some of the most consequential funding in the history of gravitational physics came from a grieving man who needed an enemy he could fight. He could not fight water, he could not fight death, or chance, or the moment his sister's hand slipped under. So he chose to fight the force itself, and because he was rich, he could afford to declare that war in the most literal way imaginable. Babson genuinely believed that gravity could be conquered the way earlier generations had conquered other forces of nature. He looked at electricity, which within his own lifetime had gone from a mysterious spark to a tamed servant lighting entire cities, and he asked why gravity should be any different. If we could insulate against electricity, if we could build materials that block it and reflect it and store it, then surely, with enough effort and enough money, we could do the same for gravity. We could build a substance that gravity does not pass through. We could make a shield. And with a shield against gravity, everything changes. Objects could be made to float. Flight would cost almost nothing. The drowning could be lifted from the water. To Babson, this was not a fantasy. It was an engineering problem that the world had simply been too distracted to solve. He even wove gravity into his broader philosophy of life, sometimes connecting Newton's action and reaction to human will, to consciousness, to a kind of moral force running through the universe. These ideas struck most physicists as somewhere between quaint and absurd, and they were one reason the professional community kept its distance from him in the early years. Here was a man with no training in relativity, who spoke of gravity as a personal enemy and mixed it with metaphysics, and who wanted to fund a search for something the theory itself suggested was impossible. To a physicist, in 1948, Roger Babson looked like exactly the kind of wealthy eccentric that a serious scientist should avoid. But that judgment, reasonable as it was, missed something. Babson had money, real money, and he had decided to spend it on gravity at the precise historical instant when no one else would. The universities had abandoned the subject. The government was pouring everything into the atom, and into that silence walked a grieving businessman with a fortune and a vendetta, ready to pay people to think about the one force that everyone else had given up on. The question was what he would build with that money. And in 1948, the year he published the essay about his sister and the dragon, Roger Babson founded an organization to carry his war forward. He gave it a plain and serious-sounding name, the Gravity Research Foundation, and he set it loose upon the problem that had haunted him his entire life. He wanted insulators against gravity. He wanted reflectors. He wanted absorbers. He wanted, in the end, a way to switch the dragon off. What he actually created was something he never intended and never fully understood. He thought he was building a foundation to defeat gravity. He was in fact building one of the strange and unlikely engines that would help bring the science of gravity roaring back to life. And it began, absurdly and wonderfully, with a small town in New Hampshire, chosen partly because it was far enough from any city to survive an atomic bomb. Part 4. A foundation built to defeat gravity. In 1948, Roger Babson established the Gravity Research Foundation in the small town of New Boston, New Hampshire. The location itself tells you something about the mind behind it. The town was chosen, at least in part, because it sat far enough from any major city to survive the fallout from a nuclear attack. This was the dawn of the Cold War, and Babson, ever the forecaster, was hedging against the end of the world. He wanted his gravity research to outlast the bomb. There is something almost touching in that. A man so certain that conquering gravity mattered to the future of humanity that he located his foundation where it might endure a nuclear exchange. The foundation's stated goal was exactly what you would expect from Babson, and exactly what made professional physicists wince. It set out to discover insulators, reflectors, and absorbers of gravity. The dream, in plain language, was a gravity shield. Babson wanted a material you could place between an object and the Earth so that the object would stop being pulled down. He often pointed to the story of electricity as his model and his inspiration. His friendship with the great inventor Thomas Edison had left a lasting mark on him, and he framed gravity as the next great force awaiting its Edison, the next invisible power that clever, practical people would learn to harness and switch on and off at will. If electricity could be tamed, why not gravity? All it needed, he believed, was attention and money. To the physics community, this was close to nonsense, and they said so. The whole idea of a gravity insulator ran against the grain of everything Einstein's theory implied. You cannot, in the standard understanding, build a wall that gravity does not cross, for reasons we will explore in detail later, reasons buried in the underlying structure of the theory. And so the Gravity Research Foundation, in its earliest years, was treated as a joke, a rich man's folly, the sort of thing that gave outsiders funny ideas about what science was for. It attracted crank letters and dubious inventors. It gave off the unmistakable odor of pseudoscience. Any serious physicist who valued his reputation kept his distance. But Babson, whatever his blind spots, was not a fool about people, and he did something clever, something that would matter enormously in the long run. Rather than relying only on the strength of the anti-gravity dream, which repelled scientists, he created a mechanism to draw them in on their own terms. In 1949, the Gravity Research Foundation launched an annual essay contest. It was open to physicists all over the world. It offered cash prizes, real money, to whoever wrote the best short essay on the subject of gravitation. And crucially, over time, it stopped demanding that those essays be about anti-gravity at all. It simply asked for good thinking about gravity. Now, at first, this contest carried all the stigma of its parent foundation. In the beginning, the prompts leaned toward Babson's obsessions, toward the practical control of gravity, and the results were often exactly the fringe material you would expect. Serious scientists stayed away. The contest looked like a magnet for cranks, and one of the most famous skeptics of the century took direct aim at it. Martin Gardner, the celebrated writer who spent his life debunking pseudoscience and bad reasoning, poured scorn on the whole enterprise. He called the essay contest, in memorable words, perhaps the most useless scientific project of the 20th century. From the outside, that verdict looked entirely fair. And yet something unexpected was about to happen, something that would slowly transform this ridiculed contest into one of the quiet engines of modern physics. To understand it, you have to understand the psychology of scientists, which is more human than we usually admit. Physicists, like everyone else, care about reputation. Most of them will not associate with a project if they see other respected minds fleeing from it. Prestige, in science, is contagious in both directions. A field that respectable people are abandoning becomes a field that respectable people avoid, and the avoidance feeds on itself. But the reverse is also true. If one truly credible physicist is willing to stand near a project, others become willing too. Someone has to be brave enough, or curious enough, to be first through the door. Babson's money created the door. It offered a prize, a platform, and a small pool of funding for a subject that the rest of the world had abandoned. What it needed was for someone with genuine scientific standing to walk through and, in doing so, tell the rest of the community that it was safe to follow. And in the early 1950s, that person arrived, though not at all in the way Babson would have wanted. The physicist who legitimized the Gravity Research Foundation did so by winning its top prize with an essay that tore Babson's entire dream to pieces. Before we get to that beautiful irony, it is worth pausing on what these organizations actually did, because it was more than handing out checks. The Gravity Research Foundation, and the sister institution that would soon follow it, became genuine hubs. They ran theoretical studies, they designed experiments, they organized meetings and published reports. They gathered scattered, isolated researchers who had been quietly working on gravity in the shadows and gave them a place to find one another. In an era when the subject had no natural home in the universities and no friend in the government, these privately funded outfits became, improbably, the places where the physics of gravity could still be done. And the patrons were not distant donors writing checks from afar. Babson was personally, passionately involved. He selected the researchers and institutions he funded with care, favoring those who shared his interest in gravitation and applying his own idiosyncratic filters along the way, including, memorably, a preference for locations far enough from major cities to survive a nuclear strike. His private patronage was, for physics, genuinely unprecedented. In those years, research money came almost entirely from two sources, from student tuition and from the government, and neither of them usually dictated a specific direction of study. Donors gave to universities in general. They rarely said, "Spend this on gravity and nothing else." Babson did exactly that. He aimed his money like a rifle at a single problem. And in doing so, he became something new in the landscape of science, a private patron steering research against the current of his entire era. It is worth pausing to appreciate just how unusual that was, because it is easy to skate past. In the whole ecosystem of 1950s physics, the flow of money was impersonal and diffuse. A government agency funded broad programs. A university spread its resources across departments. Almost no one reached in and said, "I want this specific unfashionable question studied by these specific people, and I will pay for it myself." Babson did, and so, soon after, did the second patron we are about to meet. Together they invented a kind of directed private patronage in physics that barely existed before them, and in doing so they proved something that the field has never quite been comfortable admitting, that a determined outsider with money can keep an entire branch of science breathing when the professionals have stopped. And look at who eventually passed through the doors that money held open. Over the years, the essay contest would draw submissions and prizes from a roster that reads like the founding generation of modern gravitational physics: Bryce and Cecile DeWitt, Richard Arnowit and Stanley Deser, whose initials would one day be stamped on a formalism every relativist learns, Philip Morrison and Thomas Gold, John Wheeler, who would give us the phrase black hole, Robert Dicke, and later, again and again, Stephen Hawking and Roger Penrose. These were not cranks writing to a crank foundation. These were, in many cases, the people who would rebuild the entire science of gravity. And the strange little contest that gathered them had been founded so that a grieving businessman could search for a way to hold the drowning up out of the water. That steering had consequences that Babson could never have foreseen and would probably not have recognized. He wanted a shield against the dragon. What his money actually did was keep a fragile, fading field alive long enough for the right minds to gather. It funded thinking about gravity when no thinking about gravity was being funded anywhere else. And the man who would prove Babson most spectacularly wrong, who would win his prize by demolishing his dream, would also become one of the towering figures in the revival of the very science Babson had accidentally rescued. His name was Bryce DeWitt, and in 1953 he sat down to write an essay that would change the reputation of the Gravity Research Foundation forever by telling Roger Babson, in rigorous and unanswerable detail, that everything he wanted was impossible. Part 5. The Essay That Killed the Dream and Started Another. Bryce DeWitt was a young American physicist with a rare gift, the ability to hold the fearsome mathematics of general relativity in his head and actually make it move. He was one of the small number of people in the world at that time who took gravity seriously as a living scientific problem rather than a finished monument, and in 1953 he entered the Gravity Research Foundation's essay contest with a piece of writing titled New Directions for Research in the Theory of Gravitation. He won first prize. Here is the delicious part. DeWitt's winning essay was, at its core, a demolition of the very reason the foundation existed. Babson had built his entire enterprise on the belief that gravity could be shielded, reflected, and absorbed, that a gravity insulator was waiting to be discovered. DeWitt used his prize-winning essay to explain, carefully and rigorously, why none of that is possible. He flatly rejected the idea of gravity insulators, reflectors, and absorbers. He took Babson's dearest hope and showed, from the structure of the theory itself, that it could not be built, and the foundation gave him its top award for doing so. Think about how strange that is. An organization founded to defeat gravity handed its highest honor to an essay proving that gravity cannot be defeated. It is as if a society dedicated to building a perpetual motion machine gave its grand prize to the clearest possible proof that perpetual motion is impossible. And yet this was not a humiliation for the foundation, it was its salvation. Because the moment a physicist of DeWitt's caliber engaged seriously with the contest, Even in order to tear down its premise, the contest stopped looking like a crank magnet and started looking like a place where real physics happened. This is the psychology we talked about, playing out in real time. DeWitt was credible. He was rigorous. He was exactly the kind of scientist whose presence gives other scientists permission. Once he had won and been taken seriously, the essay contest began, slowly, to shed its reputation as a joke. Other capable physicists started to enter. The prompts drifted away from anti-gravity fantasies and toward genuine open questions in gravitation. Over the following years and decades, the roster of participants and winners came to read like a roll call of the greatest names in the field. And the whole transformation turned on a single perfect irony, that the foundation devoted to conquering gravity became respectable precisely because it rewarded a man for proving that gravity cannot be conquered. But DeWitt's essay did something even more important than rescuing a contest. Buried inside that refutation was a construction. In explaining why you cannot shield gravity, DeWitt was forced to think hard about how gravity actually behaves at the most fundamental level, and in doing so, he laid down some of the earliest serious groundwork for what we now call quantum gravity, the attempt to describe gravity in the language of quantum field theory that governs all the other forces. He would go on to become one of the central figures in that quest for the rest of his life. His name is attached to one of its foundational equations. He was also the physicist who rescued another radical idea from obscurity, the many-worlds interpretation of quantum mechanics, the astonishing proposal that every quantum possibility plays out in its own branching version of reality. When you hear the phrase many worlds today, you are hearing an idea that Bryce DeWitt championed and popularized. His fingerprints are on the hardest question in the whole enterprise too. Working with the physicist John Wheeler, DeWitt helped write down an equation that tries to describe the quantum state of the entire universe, gravity and all, an equation that still bears both their names. And that equation revealed something so strange that physicists are still arguing about it. When you carefully combine general relativity with quantum mechanics at the level of the whole cosmos, the variable we call time seems to quietly disappear from the mathematics. The equation describes a universe that, in some profound sense, simply is, rather than one that flows. Physicists call this the problem of time, and it is one of the most vertiginous puzzles in all of science. The possibility that time as we experience it is not fundamental at all, but something that emerges from a more fundamental, timeless structure. That puzzle sits at the frontier of physics to this day, and a crucial early piece of it was worked out by the same man who won an anti-gravity contest by proving anti-gravity impossible. The threads keep tying themselves into knots too perfect to invent. So the man who won Babson's anti-gravity prize by killing the anti-gravity dream was, at the same moment, quietly helping to found the modern science of gravity and carrying one of the strangest ideas in all of physics into the light. This is the pattern that will repeat again and again in our story. The crank enterprise keeps producing real science almost in spite of itself because it keeps paying brilliant people to think about gravity, and brilliant people, once they start thinking about gravity, cannot help but discover true and lasting things. There is a human weight to Bryce DeWitt that deserves a moment of stillness, because he is the honest heart inside this whole strange affair. Picture him as the person who stood at the door. Around him was an enterprise built on grief and eccentricity, and a fantasy that could not be built. He did not pretend the fantasy was real. He said, plainly and publicly, that it was impossible, and he won the enemy's own prize for saying it. And then he spent the rest of his life doing the real thing, the hard, patient, genuine physics of gravity, the work that would actually matter. Later in this story, after the second of our two patrons had died, a memorial chair would be established in that patron's name, and it would be Bryce DeWitt who occupied it. And it was through that chair, funded in the name of a man who chased flying saucers, that one of the most important physicists of the 20th century would be brought to Chapel Hill. DeWitt is the living proof that something true and enduring can grow directly out of something absurd. We should be careful, though, not to make him a saint who merely tolerated fools. DeWitt took the money, he engaged with the foundation, he accepted the prize and the platform it offered. He understood, perhaps better than anyone, that the anti-gravity dream was hopeless, and he also understood that the money attached to that hopeless dream was, at that moment in history, some of the only money in the world willing to flow toward gravity at all. He was not naive. He was making a bargain, the same bargain that a whole generation of gravity researchers would soon make. That if wealthy eccentrics wanted to fund serious thinking about gravity for the wrong reasons, then serious thinkers should take the funding and do the right work with it. That bargain is the quiet moral engine of the Renaissance we are building toward. And it was about to get much larger, because Roger Babson was not the only rich man in America who had become fascinated by the idea of defeating gravity. While Babson worked from his foundation in New Hampshire, a second wealthy patron was watching the skies over North Carolina, a man of a very different temperament, drawn to gravity not by grief but by wonder, by flying saucers, by the intoxicating possibility that anti-gravity might be not a fantasy, but the next great frontier of flight. His name was Agnew Babson, and where Babson had built a foundation, Babson would build an institute, staff it with genuine physicists, and then, in secret, keep chasing the dream that his own institute publicly denied. Part 6. The Second Man with a Fortune and a Fixation. Agnew Babson was born in 1915, the same year Einstein completed general relativity, in Winston-Salem, North Carolina. He was an industrialist, a man who had taken his family's air conditioning business and grown it into a thriving company that built aeronautical equipment. He was wealthy, energetic, and restless, and unlike Babson, his fascination with gravity did not come from loss. It came from something closer to pure fascination, the intellectual thrill of a problem that seemed to sit right at the edge of the possible. Where Babson's engine was grief, Babson's was wonder, the same wonder that keeps you listening to a story like this one at the edge of sleep. Babson was, by temperament, a man who looked up. He was a private pilot who loved to fly. He was an amateur astronomer who watched the night sky. And in the mid-1950s, he took part in something called Operation Moonwatch, a program run by the Smithsonian Astrophysical Observatory that recruited ordinary amateur observers to track the first artificial satellites as they crossed the sky. This was the age when human machines first began to circle the Earth, and Babson was one of the many enthusiasts around the world who trained their eyes upward and watched those tiny points of light move against the stars. Watching the skies, in that Cold War moment, blurred easily into other kinds of watching, into the era's fever of flying saucers and unexplained objects, and the sense that the sky was full of possibilities no one fully understood. It is hard, from where we sit now, to fully recover the atmosphere of those years, but it is worth trying, because it explains so much about why anti-gravity felt not like a fantasy, but like a frontier waiting to be crossed. The 1950s were a decade drunk on the impossible becoming real. Within a single lifetime, humanity had gone from horse-drawn carriages to aircraft that broke the sound barrier. The atom had been split. Rockets were climbing toward space. Radar and jet engines and early computers were reshaping the world at a dizzying pace, and the skies were full of reports of strange craft that seemed to move in ways no known aircraft could manage, hovering, darting, accelerating without any visible means. In a decade like that, it did not feel absurd to think that gravity might be the next barrier to fall. If we could fly faster than sound, why not learn to fly without weight at all? The flying saucer reports and the anti-gravity dream fed each other. each making the other feel plausible. For a man like Babson, a builder of aircraft who spent his nights watching the sky, the idea that gravity itself might soon be conquered was not lunacy. It was the natural next step in a decade where every next step had come true. It was against this backdrop that Babson developed his own obsession with anti-gravity. To him, it was not a grim vendetta, but a frontier. If you could control gravity, you could fly without wings, without fuel, without the brutal energy cost that chains every aircraft to the ground. You could build craft that rose and hovered and darted the way the rumored flying saucers were said to move. For a man who built aeronautical equipment for a living and spent his nights watching things move across the sky, the dream of anti-gravity flight was almost irresistible. It promised to rewrite everything he knew about what a machine could do. But Babson was cleverer, or at least more strategic, than a simple dreamer. He had watched what happened to people who chased anti-gravity openly. He had seen the ridicule that clung to Babson's foundation, the scorn of men like Martin Gardner, the way serious physicists recoiled from anything with the words anti-gravity attached. He understood that if he wanted real scientists to work near his obsession, he could not lead with the obsession itself. He had to build something respectable, something that credible physicists could join without embarrassment, and then pursue his true interest quietly, in the background. So in 1955, the year Einstein died, Agnew Babson founded the Institute of Field Physics at the University of North Carolina at Chapel Hill. This was a genuine academic research center devoted to gravitation and to the search for a unified theory of the forces of nature. And to run it, Babson did something shrewd. He went after the best. He recruited Bryce DeWitt, the very physicist who had won Babson's prize by demolishing the anti-gravity dream, along with DeWitt's brilliant wife and collaborator, the physicist and mathematician Cecile DeWitt Moret. Together, these two would give the Institute real scientific weight, and Cecile in particular would soon organize the single most important event in this entire story. Consider the layers of irony stacking up here. Babson wanted anti-gravity. To pursue it, he built a respectable institute. To make the institute respectable, he hired the man most famous for proving anti-gravity impossible. And that man, and his wife, would use the institute Babson built for his impossible dream to help ignite the real revival of gravitational physics. The dreamer's money and the skeptic's rigor were now bound together in a single organization, each using the other, and out of that tension, something extraordinary was about to emerge. The Institute even developed a kind of public defense mechanism, a formal statement it would attach to its publicity. This protection clause, as it was known, made clear that the work conducted at the Institute of Field Physics was based on the accepted Newton-Einstein analysis of gravity and was not associated with anti-gravity. In other words, the Institute publicly disavowed the very thing its founder privately craved. On paper, it was a serious center for mainstream gravitational research. In Babson's heart, and in his own private laboratory, the old dream burned on undimmed. Because that is the part that makes Babson more than a footnote. Even as his institute produced legitimate physics, Babson himself never let go of anti-gravity. He kept pursuing it directly, personally, with his own hands and his own money, in a laboratory setting, chasing the dream of lift. He teamed up with an inventor named Thomas Townsend Brown, a man who claimed to have discovered a genuine anti-gravitational effect, and together they tried to make objects rise using enormous electrical forces. Babson wanted to see something float. He wanted to witness, with his own eyes, a machine defeating the force that held everything down. And this is where the physicists he had hired would be pulled into an awkward position. Babson's claims of achieving lift were dramatic enough to draw attention, and to test them, some of the most formidable scientific minds of the age would be called in to look. Bryce DeWitt would be asked to evaluate the devices. So would Edward Teller. one of the architects of the hydrogen bomb, a man not known for gentleness toward bad physics. These were not people who would be fooled by a parlor trick. When they examined what Babson was doing, they would deliver a verdict that was polite, precise, and devastating. To understand that verdict, and to understand the strange, humming, dangerous laboratory where Babson chased his dream, we need to walk into the room itself. We need to stand where a young physicist named Louis Witten once stood, just inside the door, looking at 150,000 volts strung across a meter of open air, and realizing in a single glance that what he was seeing was not the defeat of gravity at all. It was something far more ordinary and far more dangerous. Part 7. 150,000 volts. Step into the laboratory with me for a moment, and let it be the present tense, because the best way to understand what Babson was chasing is to stand inside the room where he chased it. The air has a faint metallic smell, the sharp scent of ozone that means electricity is doing something to the air itself. There is a low hum you feel in your teeth before you consciously hear it. In the center of the room sits the apparatus, and strung across it, across roughly a single meter of open space, is a difference in electrical charge of about 150,000 volts. An operator works the equipment, careful, focused, and there, just inside the doorway, stands a young physicist named Louis Witten, taking it all in and quietly understanding that something is wrong. Witten was an authority on gravitation, a serious scientist, and later in life he would become known to the wider world as the father of Edward Witten, one of the most celebrated theoretical physicists alive. But on this day, he is simply a careful observer in a dangerous room, and his trained eye catches a detail that gives the whole thing away. He knows how strong electrostatic fields behave. He knows that when you are dealing with such enormous voltages, safety demands that there be no sharp points anywhere in the apparatus, because sharp points concentrate the electric field and invite it to leap and discharge. Everything, in a properly designed high-voltage setup, should be smooth and curved. And as Witten looks around Babson's laboratory, he sees that nothing is curved. The sharp points are everywhere. This is not, he realizes, a happy place. It is a hazardous one, a room where the physics on display is not the gentle defeat of gravity, but the raw, brute force of electric charge straining against the air. That detail, the absence of curves, is the whole story in miniature. Babson believed he was watching gravity being overcome. What Witten saw was a man playing with a very large electrostatic field and mistaking its effects for something they were not. Because when the physicists were formally called in to evaluate the devices, when Bryce DeWitt and Edward Teller turned their considerable minds to the question of whether Babson and Thomas Townsend Brown had actually achieved anti-gravity, they reached a clear and unglamorous conclusion. The lift was almost certainly electrostatic. It had nothing to do with gravity at all. Here is what was really happening. Thomas Townsend Brown had built devices, essentially high-voltage capacitors, that did appear to move when powered up. Brown claimed this motion was a genuine anti-gravitational effect, a sign that electricity and gravity were secretly linked and could be made to push against each other. This claimed phenomenon even acquired a name, the Biefeld-Brown effect, and it captured imaginations for decades. But the mundane truth is that when you place an enormous voltage across a device shaped like Brown's, you ionize the air around it. You strip electrons from air molecules and hurl the resulting charged particles away, and that stream of charged air, that ion wind, produces a thrust. The device is not defeating gravity. It is essentially blowing air, very energetically, using electric fields to make a wind you cannot see. We can be quite certain of this today, because the effect is easy to reproduce. Hobbyists build small, light devices called lifters that use exactly this principle, and they do rise into the air on a whisper of ion wind when you feed them tens of thousands of volts. But they share a fatal tell with Brown's original devices, the same tell that would betray any false claim of anti-gravity. They do not work in a vacuum. Remove the air, and the lift vanishes completely, because there is no longer any air to ionize and throw. A true anti-gravity device would work anywhere, in air or in the emptiness of space, because gravity is everywhere. A device that only works when there is air to push against is not fighting gravity. It is just a very fancy fan. This single test, the vacuum test, is the quiet executioner of nearly every anti-gravity claim ever made, and it is worth carrying with you, because it is a beautiful example of how science separates a real effect from a wished-for one. Gravity does not care whether there is air in the room. It pulls on the astronaut in the vacuum of space, exactly as it pulls on you in your bed. So any genuine anti-gravity device would have to work in a vacuum, where there is nothing to push against, no air to ionize, no wind to make. The instant you put one of these miraculous lifters inside a sealed chamber and pump the air out, the miracle stops. The thrust vanishes, because the thrust was never gravitational, it was aerodynamic all along, a breeze of charged particles that needs air the way a sail needs wind. Brown's devices, and Babson's, would have failed that test, and the physicists who examined them understood exactly why. What looked like the future of flight was, in the cold light of a vacuum chamber, a demonstration of a phenomenon that had nothing to do with the force it claimed to defeat. And still sit with how easy the self-deception was, because it is not a story about stupidity. It is a story about hope, and hope is not stupid. When you want something badly enough, when you have staked your fortune and your reputation and years of your life on a dream, ambiguous evidence has a way of arranging itself into the shape of your wish. Babson saw a device rise, and he saw salvation, because salvation was what he was looking for. It took the trained, slightly detached eyes of physicists who had no stake in the dream, who noticed the sharp points and thought about the vacuum, to see the ordinary truth underneath the extraordinary hope. That is, in the end, what science is for. It is the discipline of not letting your longing decide what is real. So Babson's private dream, pursued with real money and real voltage and real hope, collided with the same wall that every anti-gravity dream eventually hits. The physicists were kind but firm. What looked like a miracle was electrostatics. What looked like the defeat of gravity was charged air in motion. The dragon, to borrow Babson's word, remained exactly as strong as it had always been. And yet, notice what did not happen. The dream failing did not make the enterprise worthless. This is the pattern again, and it is worth naming clearly, because it is the secret logic of this entire history. Every time the anti-gravity dream was tested, it failed, and every time it failed, it left real physics behind. To evaluate Babson's devices, you needed genuine experts thinking hard about gravity and electromagnetism. To explain why the lift was electrostatic, you had to understand the real relationship between those forces. The false dream kept summoning true expertise, and true expertise, once summoned, kept doing lasting work. There is a quiet human sadness in that laboratory, and it is worth honoring rather than mocking. Babson was not a stupid man. He was a successful industrialist, an accomplished pilot, a serious enthusiast who had poured his fortune and his passion into a beautiful idea. And the beautiful idea was wrong. Standing in that humming, dangerous room, he was watching charged air and seeing salvation. He wanted so badly for the machine to be defeating gravity that he could not quite see that it was only stirring the wind. The self-deception is completely human. Most of us have wanted something to be true so badly that we half convinced ourselves it was, at least for a while, at least in a dim room where the evidence was ambiguous and the hope was bright. But the physicists could not unsee what they saw. Once DeWitt and Teller and Witten had looked at the apparatus, Once they had noticed the absence of curves and understood the ion wind, the verdict was fixed. Anti-gravity, in Babson's laboratory, was not happening. It was not going to happen there, and as we will see, the underlying structure of physics itself suggests it was never going to happen anywhere in the way he imagined. And still, remarkably, the dream did not die when the lift was debunked. It spread. Because word of anti-gravity, of the tantalizing possibility that gravity might be controlled, had begun to drift out of the private laboratories and into something much larger and more powerful. It drifted into industry. It drifted toward the great aircraft companies and the emerging aerospace giants of the Cold War, corporations with money and ambition far beyond anything a single wealthy patron could muster. Anti-gravity, as one physicist would later put it in an unforgettable phrase, was in the wind. And where a private dreamer's fortune had helped keep a fading science alive, now the enormous resources of American industry were about to circle the same impossible flame. Part 8. Anti-gravity in the wind. By the mid-1950s, the dream of controlling gravity had escaped the studies and laboratories of individual enthusiasts and begun to circulate through the corridors of American industry. This was the height of the Cold War, an era when aircraft companies were becoming aerospace companies, when rockets were replacing propellers, and when it seemed, for a brief and heady moment, that almost anything might be possible if you threw enough money and talent at it. The nation had split the atom and built machines that could fly faster than sound. Why not gravity next? Why not a craft that simply switched off its own weight? The company at the center of this part of the story was the Glenn L. Martin Company, a major aircraft manufacturer that, after a long series of mergers over the following decades, would eventually become part of the corporation we know today as Lockheed Martin. In 1955, inspired by the same currents that moved Babson and Babson, the Martin Company established its own research center, an institution meant to be an industrial version of the famous Institute for Advanced Study in Princeton, the legendary home of Einstein and other great minds. The Martin Company's version was called the Research Institute for Advanced Studies. The idea was to create a place where theoretical discoveries could be turned into practical technology, where the most fundamental science might feed directly into what a company could build. And to help run it, to help find and hire the researchers who would fill it, the Martin Company turned to a gravitation expert. It hired Louis Witten, the same careful physicist who had stood in Babson's dangerous laboratory and seen through the illusion of the ion wind. Witten became a key figure at the Industrial Institute, one of the people responsible for identifying talented scientists and bringing them in, at a time when this kind of directed corporate recruitment in physics was highly unusual. He helped organize the place, helped arrange its funding, helped connect the right people to the right problems. Witten later gave a first-hand account of what it was like to work there, and his words capture the strange atmosphere of the moment perfectly. There was, he said, a new thing in the wind at the time, and that thing was anti-gravity. He learned quickly how to navigate the company's hopes. He understood that he was supposed to talk about gravity, the real, established science, while the executives around him would keep asking about anti-gravity, the dream. And he developed a diplomatic response, a way of holding both realities at once without lying to anyone. He would tell them, in effect, that we have only just begun to truly learn about gravity, and that if there turned out to be anything to anti-gravity, well, it would come along in time. It was a gentle deferral, a way of taking the dream seriously enough to keep the funding flowing while quietly steering the actual work toward legitimate science. That single sentence, anti-gravity was in the wind, tells you almost everything about how close the fringe sat to real power in those years. This was not a couple of eccentric millionaires anymore. This was a major aircraft manufacturer, a company building the rockets that would one day carry payloads into space, taking the possibility of gravity control seriously enough to hire experts and fund an institute partly in its shadow. A magazine article in 1958 openly reported that controlling the force of gravity for propulsion was among the unorthodox goals of the Martin Company's new research institute. The dream had gone corporate. It had acquired budgets and letterhead, and the interest of men who built machines for the military. The industrial money reached in surprising directions. The institute even contracted a German physicist named Burkhard Heim, a brilliant and tragic figure who had been badly injured and left blind and disabled by an explosion during the war, and who had developed his own ambitious and highly unconventional theory that tried to unify all the forces of nature in a higher dimensional space. Heim's ideas were, and remain, far outside the mainstream of physics. They have never been validated, never been meaningfully taken up by the broader physics community, and never produced a confirmed prediction. But in the fevered atmosphere of the anti-gravity years, a theory that promised a route to gravity control was worth a contract, and so Heim's exotic mathematics found a brief home inside an American aerospace institute. And running quietly beneath all of it was a thread that connects this obscure corner of Cold War industry to one of the most famous names in modern physics. Louis Witten, the man who helped build the Martin Company's institute, who saw through Babson's ion wind, who learned to talk about gravity while the executives dreamed of anti-gravity, was the father of Edward Witten. And Edward Witten would grow up to become perhaps the single most influential theoretical physicist of his generation, the towering figure of string theory, a man whose work sits at the absolute center of the modern attempt to unite gravity with the quantum world. The father spent the anti-gravity years inside an aerospace company, chasing a dream that could not be built. The son would spend his life on the real, profound difficulty of understanding gravity at its most fundamental level. The thread runs unbroken from a humming Cold War laboratory to the frontier of physics today. But we should be honest and clear-eyed about what all this industrial interest actually amounted to, because this is exactly the point where the true story and the conspiracy story part ways. There is a durable legend that industry and the military secretly discovered working anti-gravity in the 1950s and then buried it. That companies like the Martin Company and General Dynamics and even computing giants found the secret of gravity control and hid it away in classified programs. The documented reality is far more ordinary and, if you sit with it, far more interesting. The companies explored anti-gravity because the potential payoff was enormous. A company that could build a craft that defeated gravity would own the future of flight. Serious physicists evaluated the claims, and the claims did not survive the evaluation. There was no working device to bury. There was a speculative bubble, inflated by hope and money, that quietly deflated when the physics refused to cooperate. But notice, before we leave the corporate institutes behind, what the bubble did on its way up and down, because this is the underlying pattern of our story showing itself yet again. The interest of a major aircraft company meant real money, and real money meant that serious gravitation physicists were hired, funded, and gathered, even in service of a goal that would never pan out. The same lesson we drew earlier returns here with full force. Research follows funding, and funding, in this case, was flowing toward gravity for entirely the wrong reason. The executives dreamed of propulsion. The physicists took the salaries and did real physics, and so, once more, an impossible dream became a paymaster for genuine science. It is almost a law of this history. Point enough money at gravity, for any reason at all, sane or delusional, and you will end up funding people who cannot help but learn true things about it. The wrongness of the motive does not contaminate the rightness of the discovery. That is a strange and slightly unsettling fact about how knowledge actually gets made, and it runs directly counter to the tidy story we usually tell ourselves about science advancing on pure curiosity alone. Louis Witten's own memory says it best. He was told to talk about gravity, not anti-gravity. And the standing promise was that if there was ever anything to anti-gravity, it would come along. It never came along. It never came along because, as the physicists kept discovering every time they looked closely, the underlying structure of the theory of gravity seems to forbid exactly the thing the dreamers wanted. To understand why, we have to leave the humming laboratories and the corporate institutes behind for a while, and go into the physics itself. We have to ask the real question, the one underneath the whole obsession. Why can you not switch gravity off? Why is a gravity shield not just difficult to build, but very likely impossible in principle? The answer is one of the most beautiful and humbling things in all of physics. Part 9. Why you cannot switch gravity off. To see why gravity resists every attempt to shield it, the easiest place to begin is with the force we can shield, electricity, because Babson himself always reached for that comparison, and the comparison is exactly where the whole dream falls apart. Electricity can be blocked. You can wrap a sensitive instrument in a metal cage, and the electric fields outside will not reach it. You can build insulators that electricity refuses to cross, reflectors that bounce it back, absorbers that soak it up. Babson looked at all of this and reasoned, quite naturally, that gravity should yield to the same tricks. If we could tame electricity, surely we could tame its sister force. But gravity is not electricity's sister. It is a stranger, built on entirely different rules, and those rules close every door the dreamers tried to open. The first and most fundamental reason is about a thing that does not exist. Electric charge comes in two flavors, positive and negative, and this simple fact is the source of all our power over it. Because there are two signs of charge, you can build something neutral, an object with equal positive and negative parts, and you can arrange those charges to cancel an outside field. A metal cage works because its electrons rearrange themselves to oppose whatever field you bring near it. Shielding electricity is really just the art of using one sign of charge to cancel the other. Now ask the fatal question. What is the negative version of mass? And the answer, as far as anyone has ever observed in the entire history of physics, is that there isn't one. Mass comes in only one sign. Everything pulls. Nothing pushes. There is no negative mass to place between you and the Earth. No gravitational opposite to arrange into a cancelling shield. Without two signs, there is no neutral, and without a neutral, there is nothing to build an insulator out of. The very first ingredient of shielding is simply missing from gravity. The second reason lives in the mathematics of Einstein's theory, and it is subtle and gorgeous. The equations that govern electricity, Maxwell's equations, are what physicists call linear. Linearity means, in plain terms, that solutions add up cleanly. If you have one valid electric field and another valid electric field, you can lay them on top of each other, and the combination is also valid, and the total is just the simple sum of the parts. This is precisely what lets you cancel fields, because you can add a field that is the exact negative of the one you want to block. Einstein's equations for gravity are not linear, they are non-linear, and this changes everything. Gravity, in general relativity, is generated by energy, and gravity itself carries energy, which means that gravity is a source of more gravity. The field feeds on itself. You cannot simply take two gravitational solutions and add them to get a third, because the pieces interact, they warp each other, they refuse to stay separate. And if solutions do not add cleanly, then the whole trick of cancellation, of laying down an equal and opposite field to block the one you have, stops working. The mathematics that makes electric shielding possible is exactly the mathematics that gravity does not obey. The third reason speaks the language of particles, and it comes from thinking about how forces are carried. In the quantum picture, every force is transmitted by a messenger particle. Electricity is carried by the photon, the particle of light. Gravity, if we ever fully quantize it, would be carried by a particle physicists have named the graviton, which no one has ever detected, but whose properties can be worked out from the theory. And here is the crucial difference. The photon that carries electricity is a spin-1 particle, and that spin-1 character is exactly what allows electricity to both push and pull, to have like charges repel and opposite charges attract. The graviton that would carry gravity is a spin-2 particle, and that spin-2 character has a profound consequence. It forces gravity to be purely attractive between ordinary matter. Every mass pulls every other mass, and there is no configuration of ordinary matter that produces repulsion. The spin of the messenger locks gravity into attraction and forecloses the electromagnetic trick of using opposite charges to neutralize the field. The impossibility of shielding is written into the very spin of gravity's carrier. There is something almost poetic in that. Electricity can push and pull because its messenger, the photon, is built one way. Gravity can only ever pull because its messenger, the graviton, is built another. The whole reason you can shield a wire and not a planet comes down to a difference in the spin of two particles, one of which we have measured directly, and one of which we have never even seen, and yet whose properties the theory pins down so tightly that we can already say, with confidence, that it forbids the very machine Babson spent his life and fortune trying to build. The answer to his dream was hiding, all along, in a number describing how a particle turns. The fourth reason is almost embarrassingly simple, and it is perhaps the most final of all. Everything couples to gravity. Every form of matter, every form of energy, everything that exists feels gravity and produces gravity. There is no exception, no special substance that gravity passes through as if it were not there. Think about what an absorber or a reflector of gravity would actually require. It would need to be a material that intercepts the gravitational influence and stops it, or bounces it back. But to stop gravity, the material would itself have to not participate in gravity in the ordinary way, and no such material exists, because participation in gravity is universal. You cannot build a wall that gravity does not cross, because there is no known stuff that gravity does not touch. Every brick of your would-be shield would itself feel the pull and add its own pull and pass the influence straight through. Put those four together, the absence of negative mass, the nonlinearity of the equations, the spin-2 graviton, and the universal coupling of everything to gravity, and you have as close to a proof of impossibility as physics offers for anything. This is what Bryce DeWitt understood in 1953, when he won Babson's prize by demolishing Babson's dream. The gravity shield is not merely hard to engineer, like a faster rocket or a better battery. It appears to be forbidden by the underlying structure of the theory in four independent ways at once. The dragon cannot be caged, because caging requires ingredients that gravity simply does not provide. And yet a truly honest physicist has to hold that conclusion loosely, and it is worth understanding why, because the caveats are as interesting as the rule. We do not yet possess a final, complete theory of gravity. General relativity and quantum mechanics have never been fully reconciled, and until they are, the phrase impossible in the standard framework is not quite the same as the phrase impossible in principle. History is full of things that were forbidden by the physics of one century and commonplace in the next, not because the old physics was wrong, but because it was incomplete. Consider the pattern. In the 1800s, a tiny, unexplained wobble in the orbit of Mercury looked like a minor annoyance, until it cracked open Newton's universe and delivered general relativity. The glow of hot objects, the so-called black-body radiation, was a small embarrassment that classical physics could not quite explain, until it detonated into the entire quantum revolution. A puzzling gap in the energy of radioactive decay led Wolfgang Pauli to propose a ghostly, nearly undetectable particle, the neutrino, that went unseen for more than 2 decades before it was finally caught. Again and again, The anomaly that looks like a small crack turns out to be a door. So a careful mind does not say anti-gravity is impossible, full stop. It says anti-gravity is forbidden by everything we currently understand, while quietly remembering that everything we currently understand has been overturned before. There are even hints, at the edges of modern physics, that gravity might be less fundamental than it looks. In condensed matter physics, and in the study of engineered materials called metamaterials, scientists routinely coax matter into exhibiting bizarre, effective behaviors that its raw ingredients seem to forbid, bending light backward, hiding objects, mimicking exotic physics. And there is a serious line of thought, pursued by respected physicists, that space-time and its curvature might themselves emerge from the collective behavior of some more fundamental underlying stuff, the way the smooth flow of water emerges from the chaos of individual molecules. If gravity is emergent rather than fundamental, then the rules about what can and cannot be done to it might be softer than they appear. None of this is a working loophole. No one has walked through any of these doors, but they are the reason an honest scientist keeps the word impossible in a gentle grip rather than a fist. And now, because intellectual honesty is the whole point of a channel like this, we have to acknowledge the one genuine crack in that wall, the single place where real, published physics leaves the door open a hair. In 1979, a physicist named Joël Chirc published a short paper with a wonderful title. He called it, in a spirit of self-aware daring, anti-gravity, a crazy idea? And in it he showed something remarkable. In certain advanced theories called extended supergravity, theories that weave together gravity and a profound symmetry of nature called supersymmetry, the graviton acquires companions. One of those companions is a spin-1 partner, sometimes called the graviphoton, and unlike the spin-2 graviton, this spin-1 partner can produce a genuinely repulsive contribution. It can create a real anti-gravity, a push that partially cancels the ordinary pull, at least in the mathematics. Chirc showed that in these theories, anti-gravity is not an absurdity at all, but a natural consequence of the structure. So, does that mean the dreamers were right after all? Sadly, no. And the reason why is almost poetic. Even in Chirc's theories, exploiting this effect would be catastrophically impractical. In his own framing, using it would require something like heating the vacuum itself, an act so violent and energetic that it would be destructive far beyond any technology we can imagine, and beyond the reach of any engine we could survive building. And on top of that, the beautiful supersymmetry that makes the effect possible appears to be broken in the real world, hidden or absent at the energies we can access. The door exists. It is a real door, written in real equations by a real and respected physicist. But it opens onto a furnace no one can enter. The crack in the wall is genuine, and it is also, for any practical purpose, sealed. This is what makes the physics of gravity so humbling. The reason your body stays in your chair, the reason a dropped cup falls to the floor, the reason the water once closed over Roger Babson's sister, is not some superficial fact that a clever inventor might one day switch off. It is woven into the most fundamental layers of reality we have ever uncovered, into the absence of negative mass, into the non-linear self-feeding of the field, into the spin of a particle we have never even seen, into the universal fact that everything that exists must answer to gravity's pull. Babson and Barnson spent fortunes trying to find the loophole. The loophole was never there, and in searching so hard for a door that does not open, they funded the people who would map the walls with a precision no one had ever managed before. Because here is the turn the whole story has been building toward. All that money, all that misguided obsession, all that chasing of a dream that the physics forbids, did not vanish into nothing. It gathered, at one particular moment, in one particular room, in the winter of 1957, in a conference funded by Agnew Barnson's Institute. And in that room, the science of gravity, which had been sleeping for 40 years, finally woke up. Part 10. A Room in Chapel Hill. In January of 1957, in the town of Chapel Hill, North Carolina, a group of physicists gathered for a meeting that would quietly change the course of an entire science. It was called the Conference on the Role of Gravitation in Physics, and it has been remembered ever since simply as the Chapel Hill Conference. It ran from the 18th to the 23rd of January, 6 days in the middle of a Cold War winter, and it was funded and made possible by Agnew Barnson's Institute of Field Physics, organized in large part by Cecile DeWitt Moret, with some additional support arranged through the United States Air Force. The Dreamers Institution, the one built in the shadow of an impossible dream, had convened the meeting where the real science of gravity would be reborn. To feel why this conference mattered so much, you have to remember how starved the field had been. Think back to everything we have covered. After Einstein completed general relativity in 1915, the study of gravity had gone quiet for 4 decades, and in all those years, there had been almost no great conferences devoted to it. Physics did hold famous gatherings, the most legendary being the Solvay conferences, where the titans of the field argued about the meaning of reality. But the great Solvay meeting of 1927, the one whose photograph shows Einstein and Bohr and Curie, and nearly every founder of modern physics in a single frame, was about quantum mechanics. Gravity had no equivalent. For 40 years, the people who cared about Einstein's theory had been scattered across the world, working in near isolation, rarely meeting, rarely able to argue face to face. The Chapel Hill Conference was, in a real sense, the first great gathering of the gravity community since the theory was born. It was their Solvay, 40 years late. For many of the researchers who came, it was the first time they had ever been in a room full of people who shared their obsession. Imagine spending years thinking about the curvature of space-time, with almost no one to talk to, and then walking into a conference hall and finding it full of the only other people on Earth who understood what you were working on. The isolation of the low water mark broke, all at once, in that room. Ideas that had been developing in separate minds, on separate continents, suddenly collided and combined. Connections formed that would shape the field for the rest of the century. It was at Chapel Hill, for instance, that a young Richard Feynman and the physicist we have been following, Louis Vuitton, first met. The threads of our story were literally weaving themselves together in that hall. But the conference is remembered above all for one argument, one piece of reasoning delivered in that room that settled a question physicists had been quarreling over for decades. The question was about gravitational waves, and to understand why it mattered, you have to understand that it was not at all obvious, in 1957, that gravitational waves were even real. Einstein's theory predicted them. If gravity is the curvature of space-time, and if masses can move, then a violently accelerating mass, like 2 stars whirling around each other, should send ripples outward through the fabric of space-time itself, waves of curvature spreading at the speed of light. Einstein had derived these waves from his own equations back in 1916, but he had also, over the following years, gone back and forth on whether they were physically real or merely a kind of mathematical illusion, an artifact of the particular coordinates you happen to choose to describe spacetime. This was the nagging worry that haunted the subject. In general relativity, you are free to describe events using any coordinate system you like, and sometimes a thing that looks like a wave in one coordinate system can be made to vanish by cleverly switching to another. So the terrible question hung over the field. Were gravitational waves a true physical phenomenon that carried energy across space, or were they a bookkeeping mirage that a change of perspective could erase? For decades, brilliant people could not agree. The confusion ran so profound that even Einstein himself had stumbled over it. Having predicted gravitational waves in 1916, he returned to the question 2 decades later and, for a time, convinced himself that they did not exist at all. In the mid-1930s, he wrote a paper together with a collaborator, arguing that gravitational waves were a mathematical illusion, and he submitted it to a journal. A referee pushed back, pointing out an error. Einstein, irritated, nearly withdrew it, but eventually he found the mistake himself and reversed his conclusion. If the man who invented the theory could talk himself into believing the waves were real, then unreal, then real again, you can appreciate how genuinely slippery the question was. It was not a matter of anyone being foolish. It was a matter of a subtlety so profound that the greatest mind in physics had been caught by it. That is the knot that had to be cut. And it would be cut not by a longer, more fearsome calculation, but by a picture simple enough to hold in your hand. At Chapel Hill, the ground was prepared by a physicist named Felix Pirani, who had been doing crucial work on how to describe gravity in a way that did not depend on the arbitrary choice of coordinates. Pirani explained the central role of a mathematical object called the Riemann curvature tensor, and in particular, the part of it that describes tidal forces, the stretching and squeezing that curvature produces. He gave the first correct description of how a passing gravitational wave would actually affect a set of free-floating test particles. Because the tidal effect is built from the true curvature, and the true curvature cannot be wished away by changing coordinates, Pirani's description pointed toward an answer. But it was another mind in that room who turned the insight into something no one could argue with, something so simple and vivid that it ended the debate. Let me put you in the room now, in the present tense, because this is one of those moments in the history of science that deserves to be lived rather than summarized. It is a conference hall in Chapel Hill in the winter of 1957. There is chalk dust in the air. The men in the room have spent their careers on a theory the rest of physics had written off, and they are arguing, as they have argued for years, about whether the ripples in Einstein's equations are real. And Richard Feynman, restless and brilliant, steps up and offers a picture so concrete that a child could follow it. Imagine, he says, a rigid rod. Now thread onto that rod two small beads, free to slide along it, held with just a little friction, so they can move but not too easily. Hold the rod sideways to a passing gravitational wave. What happens? The wave, as it passes, stretches and squeezes the space along the rod. The atoms of the rod are held together by strong electrical forces, so the rod itself keeps very nearly its length. But the proper distance between the two beads, the actual distance measured through the wave-warped space, oscillates as the wave goes by, so the beads slide back and forth along the rod. And because there is friction between the beads and the rod, that sliding generates heat. The rod grows warm. Now feel the force of that simple picture, because everyone in the room felt it. If a gravitational wave can make beads slide against a rod, and that sliding produces heat, then the wave has done work. It has deposited energy, and anything that carries energy and can do real, measurable work on real matter is not a mathematical illusion. It is physically, undeniably real. You cannot make heat appear by choosing a different coordinate system. Heat is heat. The sticky bead argument, as it came to be called, cut straight through the decades of confusion. It did not require anyone to master the fearsome tensor mathematics. It required only the willingness to picture a bead sliding on a rod and getting warm. And with that picture, the question was settled. Gravitational waves are real. They carry energy. They can, in principle, be detected, because anything that heats a bead can be caught by a sufficiently sensitive instrument. Sit for a moment with the strangeness of where this happened. The argument that convinced physicists gravitational waves were real. The argument that pointed directly toward the possibility of one day building a machine to catch them was delivered in a conference room paid for by Agnew Barnson's Institute of Field Physics. And Agnew Barnson, at that very moment, was a man who spent his private hours in a humming laboratory trying to build an anti-gravity machine out of 150,000 volts and hope. His money, chasing a dream that the physics forbids, had assembled the room in which the physics that would actually change the world was spoken aloud. He wanted to defeat gravity. What his money bought instead was the moment humanity finally understood that gravity itself sings, that it sends ripples across the universe, and that we might one day learn to listen. Among the people paying close attention to the reality of gravitational waves was a physicist named Joseph Weber, who moved in exactly this milieu. Weber took the idea seriously and did the audacious thing. He decided to try to actually detect these waves, to build a machine sensitive enough to feel the faint tremor of a passing ripple in space-time. In the years that followed, he constructed the first gravitational wave detectors, large cylinders of aluminum, sometimes called Weber bars, designed to ring ever so slightly when a gravitational wave passed through them. His early claims of detection did not hold up, and the waves turned out to be far fainter and far harder to catch than anyone had hoped. But Weber had started something. He had turned the sticky bead argument into an engineering ambition. He had asked, in effect, what if the rod and the bead were not a thought experiment, but a real machine, built as carefully as human beings can build anything, and pointed at the sky? That question would take another half a century to answer, but it began here, in the wake of Chapel Hill, in the years right after Feynman drew his beads on a rod. What we are watching, in this conference room, is the exact hinge of the entire story. Everything before it was decline and obsession and private dreaming, a field going dark. Two grieving, wandering millionaires pouring money at an impossible goal, ridicule and ion wind and voltage. But in this room, funded by that money, the direction reverses. The gravity community finds itself. The reality of gravitational waves is established. The ambition to detect them is born. From this moment forward, the story is no longer about decline. It is about a renaissance, a revival so complete that within a few decades, gravity would go from the most neglected subject in physics to one of the most celebrated, and the descendants of Feynman's bead on a rod would hear two black holes collide at the far edge of the observable universe. The dreamers had lost their war, but the science they had accidentally funded was about to win everything. Part 11. The Renaissance that reached the edge of the universe. After Chapel Hill, the dam broke. The field that had lain nearly dormant for 40 years came alive with a speed that still astonishes the historians who study it. And for the next 2 decades, general relativity produced one landmark after another, a cascade of discovery that turned Einstein's neglected theory into the beating heart of modern physics. And running quietly through that cascade, again and again, were the two strange institutions this whole story has been about: Roger Babson's essay contest and Agnew Barnson's institute, still funding, still gathering, still paying brilliant people to think about gravity. Consider the young Stephen Hawking. Long before he became the most famous scientist on Earth, before the wheelchair and the synthesized voice, and the best-selling book that sat on millions of shelves, Hawking was a brilliant graduate student, working on gravity in the early 1960s. And some of his earliest ideas, the seeds of what would become his monumental work, appeared first not as formal papers in prestigious journals, but as essays submitted to the Gravity Research Foundation's contest, the very contest Babson had founded to chase his impossible shield. Hawking won that contest more than once. Several of his ideas surfaced there in an early speculative form, sometimes even before the famous theorems that would later make his name. Think about what that means. The freedom of the essay format, the permission to be bold and unfinished and speculative, may have helped catalyze the young Hawking's thinking into rigorous shape faster than the ordinary machinery of science would have allowed. And that permission existed because a grieving businessman had once decided to make war on gravity. We cannot know exactly how much the contest shaped the timing of Hawking's genius, but the venue was there when he needed it, and it was there because of Babson's money. Hawking was only one figure in a gathering flood. The list of what the Renaissance produced reads like the foundation of everything we now know about gravity and black holes. There was the work of Arnowit, Deser, and Misner, three physicists whose reformulation of general relativity, known forever after by their initials as the ADM formalism, gave scientists a powerful new way to think of spacetime as evolving through time, a framework essential to nearly all modern work in the field, including the computer simulations that would eventually be needed to understand colliding black holes. And two of those three men, Arnowit and Deser, had themselves been winners of Babson's essay contest. There was Reggie calculus, developed around 1961, a beautiful method for approximating the smooth curved spacetime of general relativity with a kind of faceted, triangulated structure, making the impossible mathematics tractable for computation. There was the Bondi-Sachs framework of 1962, which finally clarified how to describe gravitational radiation escaping to infinity, nailing down the energy that Feynman's beads had proven the waves must carry. And then, in 1963, came one of the most celebrated results in the history of the field. A mathematician named Roy Kerr found an exact solution to Einstein's fearsome nonlinear equations describing a spinning black hole. For decades, physicists had only been able to solve the equations for a perfectly still, non-rotating mass, an idealization that describes almost nothing real, because everything in the universe spins. Kerr cracked the rotating case, and his solution turned out to describe the black holes that actually exist, the whirling monsters at the centers of galaxies, and the collapsed cores of dead stars. The Kerr solution remains one of the crown jewels of general relativity, and it emerged in the full flood of the Renaissance. 2 years later, in 1965, Roger Penrose proved the first of the singularity theorems, using elegant new mathematical techniques to show that, under very general conditions, the collapse of matter into a black hole must produce a singularity, a point where the known laws of physics break down. Working with Hawking, Penrose extended these ideas to the universe as a whole, suggesting that time itself must have begun in a singularity, the Big Bang. These theorems transformed black holes and the origin of the cosmos from speculative curiosities into rigorous consequences of Einstein's theory. Then came the 1970s, and the discovery that black holes obey laws of thermodynamics, that they have a temperature and an entropy, culminating in 1974 in Stephen Hawking's most famous result of all, the prediction that black holes are not perfectly black, that they slowly glow and evaporate, leaking energy through a subtle quantum process now called Hawking radiation. In the span of less than 20 years, gravity had gone from a dead end to the frontier where relativity, quantum mechanics, and thermodynamics all meet. The institutions kept threading through it. Remember the memorial chair, the one established in Agnew Barnson's name after his death, and occupied by Bryce DeWitt. It was through that chair, funded in the name of a saucer-watching industrialist who chased anti-gravity in a high-voltage laboratory, that Peter Higgs, fresh from proposing the mechanism that gives particles their mass and predicting the particle that would eventually be called the Higgs boson, came to spend a year at Chapel Hill in the mid-1960s. The reach of this small, strange, privately funded corner of physics kept touching the largest names and the biggest ideas of the century. John Wheeler, one of the great physicists of the era, and himself connected to this world, gave us the very word black hole, and imagined a quantum foam churning at the smallest scales of spacetime, ideas that still guide the search to unite gravity with the quantum world today. Step back for a moment and take in the sheer scale of the transformation, because it is easy to lose it in the parade of names and dates. In 1950, gravity was a backwater, a finished monument that ambitious young physicists were warned away from, a subject with almost nothing left to do. By the middle of the 1970s, barely 2 decades later, it had become one of the most exciting frontiers in all of science. Black holes had gone from a mathematical curiosity that even Einstein doubted was real to a central object of study. The birth of the universe had become a rigorous consequence of the equations. Gravity had been shown to touch thermodynamics, quantum mechanics, and the hardest questions about the origin and fate of everything. A field that had been left for dead came back, not merely alive, but flourishing, generating the ideas that would occupy the finest minds in physics for the rest of the century and beyond. And the whole revival had been midwifed, in ways large and small, by two privately funded institutions that most physicists had initially regarded with embarrassment, born from a grieving man's vendetta and a dreamer's fascination with sources. The Gravity Research Foundation even commissioned a comprehensive report on the state of the field, a survey of where gravitational physics stood and where it might go, a document that reads well to this day, more than half a century after it was written. The cranks, in other words, had not just funded the Renaissance, they had helped it take stock of itself. But the single result that most vindicates this whole improbable history was still decades away, and it grew directly out of Feynman's beads on a rod. Because Joseph Weber's ambition to actually detect a gravitational wave never died. It was passed down, refined, and reimagined by a new generation who replaced Weber's aluminum bars with something far more sensitive, laser light. The idea was to build an enormous L-shaped instrument, to fire laser beams down two long perpendicular arms, bounce them off mirrors hung at the ends, and watch for the almost inconceivably tiny change in the lengths of those arms that a passing gravitational wave would produce. This became the Laser Interferometer Gravitational Wave Observatory, and its two detectors, in Washington State and in Louisiana, each had arms 4 kilometers long. Feynman had imagined a rod with a bead that would slide as a wave passed. LIGO was that rod and that bead, rebuilt at the scale of a machine you could see from an airplane, hunting for a motion smaller than anyone had ever tried to measure. The difficulty of that hunt is almost impossible to overstate, and the road to it was long and full of doubt. Joseph Weber, the pioneer, had claimed detections back in the 1960s and 1970s that the community eventually could not confirm, and he spent his later years defending results that most physicists came to reject. For a time, the whole quest to detect gravitational waves carried a faint whiff of the same disrepute that had once clung to the anti-gravity dream, the sense that this was a fool's errand, chasing a signal too faint to ever catch. The skeptics had a point. The motion LIGO was built to detect is so unimaginably small that it beggars comparison. The arms would need to sense a change in length smaller than 1/10,000th the width of a single proton, across 4 full kilometers. That is like measuring the distance to the nearest star beyond the sun and detecting a change the width of a human hair. To do it, physicists had to isolate the mirrors from every footstep, every passing truck, every distant earthquake, every restless atom jostling with heat, and to fire laser beams of such stability that the light itself became a ruler more precise than any ever built. It took decades, it took hundreds of scientists, and enormous sums of money, and a faith, sustained across a generation, that Feynman had been right, that the bead really would slide on the rod if only the rod were sensitive enough. That faith traced straight back to the argument settled in Babson's conference room. Let me put you there for the moment it finally worked, in the present tense, because humanity waited 100 years for this, and it deserves to be felt. It is the 14th of September, 2015, more than 1 billion years ago, in a galaxy unimaginably far away, two black holes, each some 30 times the mass of the Sun, have been circling each other for eons, spiraling closer and closer, and in their final instant they collide and merge, and in a fraction of a second they convert roughly 3 times the entire mass of the Sun into pure gravitational energy, a burst so violent that for that instant it outshines, in gravitational power, every star in the visible universe combined. That energy pours out as a ripple in the fabric of space-time, a wave of pure curvature, and it races outward at the speed of light. For 1,300,000,000 years it travels, crossing the emptiness between galaxies, while on a small blue planet, life crawls out of the sea. Dinosaurs rise and fall, and a species of upright apes slowly learns to do physics. And then, on that September morning, the ripple reaches Earth. It passes through the 4-kilometer arms of the LIGO detectors, and it stretches and squeezes them by a distance smaller than 1/10,000th the width of a single proton. The mirrors move, the bead slides on the rod, and this time, the rod is a machine we built, and it is listening. The signal that came through, when the scientists cleaned it up, was a rising tone, a chirp, the sound of two black holes swinging faster and faster around each other, and then merging into one. Humanity heard it. For the first time in the history of our species, we detected a gravitational wave, the precise phenomenon whose reality Feynman had argued for with beads on a rod in a conference room that Agnew Barnson had paid for. The discovery was announced to the world, and it won the Nobel Prize in Physics. It opened an entirely new way of observing the universe, not with light, but with the tremor of space-time itself. And every bit of it traces back, through an unbroken chain, to the moment gravity science woke up at Chapel Hill, in a room funded by a man who wanted to switch gravity off. Think about what that new way of seeing actually means, because it is worth letting the wonder of it settle over you. For the entire history of astronomy, from the first person who looked up and named a star, to the great telescopes orbiting the Earth today, we have studied the universe using light, or the other forms of electromagnetic radiation that are really just light in disguise. Every image we have ever made of the cosmos has been, in the end, a picture. But a gravitational wave is not light. It is a ripple in the shape of space itself, and it passes through everything, unblocked, uncatchable by any lens, ignored by every mirror. Detecting it gave humanity a genuinely new sense, as if a species that had only ever seen the world suddenly, after millions of years, learned to hear it. Black holes, which emit no light at all, which are by their nature invisible, announce their collisions in gravitational waves. We are now listening to events that light can never show us, the mergers of dark giants in the dark of space, the tremors of the most violent moments in the universe. And the first faint note of that new music was played in a machine, descended from a bead on a rod, argued over, in a room paid for by anti-gravity money. So here is the full weight of the paradox, finally laid bare. Roger Babson wanted a shield against gravity because it drowned his sister. Agnew Barnson wanted anti-gravity flight because he watched the skies and dreamed. Neither of them got what they wanted. The shield was impossible. The flying saucer was ion wind. But the money they moved, chasing those impossible dreams, funded the essay contest that catalyzed Hawking, staffed the institute that convened Chapel Hill, and set in motion the chain of discovery that ends with humanity hearing two black holes collide 1 billion light-years away. They lost their war on gravity completely, and in losing it, they helped give us the fullest understanding of gravity our species has ever possessed. There is only one part of the story left to tell, and it is the part where the force itself, the dragon, has the final word. Because Agnew Barnson, the man who spent the second half of his life trying to defeat gravity, would meet his end in the one way that turns this entire history into something almost unbearably poignant. Part 12. The Force That Wins in the End. On the 3rd of June 1964, Agnew Barnson died in the crash of his private airplane. The man who had spent the second half of his life trying to defeat gravity, who had funded an institute in its name, who had chased lift in a laboratory humming with 150,000 volts, who had watched the skies for craft that might one day float free of the earth, fell out of that same sky and was killed by the very force he had declared war upon. There is no way to soften the irony, and perhaps we should not try. Barnson dreamed of rising above gravity, and gravity brought him down. The dragon, in the end, had the last word. I want to sit gently with that loss for a moment. because it would be easy to make it a punchline, and it deserves better. Babson was not a fool chasing nonsense. He was a man of genuine wonder, a builder, a flyer, someone who looked at the night sky and could not stop asking whether the impossible might be possible after all. He poured his fortune and his passion into a dream that the underlying structure of physics would not permit, and he never lived to see how much good that misplaced dream had done. He died in 1964, before the Kerr solution had fully reshaped our picture of black holes, before Penrose proved his singularity theorem, before Hawking radiation, decades before LIGO heard two black holes collide in a machine descended from a conference his own money had funded. He never got to know that his lost war had helped win something far greater than he was chasing. He only got the crash, and the terrible symmetry of being taken by gravity itself. And Roger Babson, the grieving forecaster who started it all, who blamed gravity for the water that took his sister and his grandson, lived on until 1967. He never got his shield. He never found the insulator, or the reflector, or the absorber. The dragon he had fought for so long was never caged, and the physics we have walked through tonight suggests it never can be, not in the way he imagined. But his foundation did not die with him. The Gravity Research Foundation still exists. Its essay contest, the one Martin Gardner mocked as perhaps the most useless scientific project of the 20th century, still runs to this day, still drawing serious physicists year after year. Its list of winners, studied with people who went on to win the Nobel Prize. The war on gravity that began in a grieving man's heart became, against every intention, one of the quiet engines that kept the science of gravity alive. Now let me return to three phrases we planted along the way, because each of them means something different now than it did when we first heard it. Remember Babson's words for gravity, his name for the force that drowned his sister. He called it our enemy number one. When we first heard that phrase, it was the war cry of a grieving man, a little wild, a little absurd, a vendetta against a law of nature. But listen to it now, at the end of the story. The enemy became the teacher. The force Babson tried to abolish turned out to be the one that gave us black holes, and the singularity at the birth of the universe, and ripples in space-time we learned to hear, and the single greatest unsolved problem in all of physics. Gravity was never our enemy. It was the greatest teacher our species has ever sat before, and Babson, in hating it, accidentally paid for the lessons. Remember too, Feynman's beads on a rod, that simple picture of a wave making beads slide until the rod grew warm. When we first heard it, it was chalk on a blackboard, a clever thought experiment to settle an argument in a room in Chapel Hill. But that bead and that rod grew up. They became a machine with arms 4 kilometers long, mirrors hanging in near-perfect stillness, laser light measuring a motion smaller than a fraction of a proton. The thought experiment became a fact about the universe. The bead slid on the rod exactly as Feynman said it would, and when it slid, humanity heard two black holes become one, more than 1 billion light-years away. What began as a way of imagining now stands as a way of listening. And remember Louis Witten's phrase for the mood of those Cold War years, when the aerospace companies leaned in and the executives dreamed. Anti-gravity, he said, was in the wind. When we first heard it, it meant the fringe rumor drifting through industry, the tantalizing hope of a machine that could switch off its own weight. But we can see now what was truly in the wind, and it was not anti-gravity. Anti-gravity never came along, just as Witten quietly predicted it might not. What was really in the wind, unnoticed by almost everyone chasing the dream, was an entire field of physics waking up from a 40-year sleep. The real thing in the air was the Renaissance itself, hiding behind the illusion, waiting for the room and the money and the minds to come together. The dreamers thought they smelled a flying saucer. What was actually approaching was the rebirth of our understanding of the cosmos. So which is the true story? Were the cranks defeated by the physics, Or was the physics rescued by the cranks? The honest answer is that both are true at once. And that is what makes this history so quietly beautiful. The anti-gravity dream failed on every front. The shield is impossible. The lift was ion wind. The suppressed secret device never existed. And yet the pursuit of that failed dream funded an essay contest, built an institute, convened a conference, and set in motion a chain of discovery that runs straight to the Nobel Prize and to a new way of seeing the universe. The wrong question, asked loudly enough and funded well enough, summoned the right answers. That is not how we like to imagine science working, but it is, sometimes, how it actually works. And underneath even that, there is a mystery still open tonight, still unsolved, still waiting, because for all that the Renaissance accomplished, gravity remains the one force we have never been able to fit into the quantum picture that governs everything else. The graviton, that spin-2 messenger particle we spoke of, has never been detected and may never be. Quantum gravity, the dream of uniting Einstein's curved spacetime with the quantum world of the very small, remains the great unfinished problem of physics, the one Murray Gell-Mann once left off his list, the one that has humbled every mind that has approached it, including some of the greatest who ever lived. And anti-gravity, the very thing Babson and Barnson chased, remains almost, but not quite, forbidden. Shirk's crack in the wall is still there in the equations, a door onto a furnace no one can enter. The war on gravity that two grieving, wondering men began was never truly won by either side. It is still being fought, quietly, patiently, in the equations, tonight, while you drift towards sleep. That is perhaps the strangest and most wonderful thing to carry with you as you rest. The force that shaped every step you have ever taken, that holds you to your bed right now, that has been with you since before your first breath, and will be with you until your last, is also the one piece of physics we have never fully understood. It is the most familiar thing in your life, and the greatest riddle in our science, both at once. Roger Babson thought of it as a dragon. Agnew Barnson thought of it as a frontier. The physicists who came after them learned to think of it as a teacher and a mystery and a kind of music the universe plays across billions of light years. And every one of those visions is, in its own way, true. There is a gentle lesson tucked inside this whole strange history, and it is the kind of thing worth carrying into sleep. We tend to believe that the great advances of science come from asking the right questions, and often they do. But sometimes they come from asking the wrong question, with enough passion and enough resources that the right people are drawn into the room, and once they are in the room, the truth begins to reveal itself, almost against everyone's intentions. Babson asked how to defeat gravity, which was the wrong question, a question the universe simply will not answer. But in asking it loudly enough, and funding it generously enough, he helped assemble the people who would ask the right ones. How do black holes form? What is a gravitational wave? What happens when we combine gravity with the quantum world? The wrong question, it turns out, can be a doorway to the right ones, if it brings the right minds together. There is something almost forgiving in that, something that says even our confusions and our griefs and our impossible hopes can, by accident, do good in the world. And so the two men who lost their war on gravity gave us, without ever knowing it, a quiet peace with the force they hated and loved. They wanted to escape gravity. What they left behind was a way to understand it, to hear it, to trace its ripples across 1 billion years of empty space. That is a better gift than the one they were chasing, and it is the gift we live inside now. Every one of us, held gently to the earth by the same force that carries the songs of colliding black holes to our listening machines. Thank you for spending this time with me, wandering through the strange and secret history of the war on gravity and the Renaissance it accidentally set free. If a slow, winding story like this one is the kind of thing you like to fall asleep to, a quiet like or subscribe, genuinely helps this channel keep going. It is a small thing for you, but it means a great deal to me, and it lets me keep making these. And remember, the next time you feel gravity gently holding you where you are, that the most ordinary force in your life is also the greatest secret in physics, and that two men once declared war on it, and lost, and in losing gave us the stars. Good night, and may you never feel the pull of gravity quite the same way again.